Okay, here we are in the lab again, and this is episode number 7 of Build Your Own Main Brain Microcontroller project. So, last time we uh, covered the oscillator and the configuration bits associated with the oscillator. And so we have to finish that, which means we have to go over the oscillator control registers, which are not the same as the configuration bit registers. The configuration bits are loaded as soon as the microcontroller is turned on. So those need to be set up first. But the control registers can be changed at any time during operation of your firmware, your real time. It can be changed in real time. So, or runtime, I should say runtime. It can be changed anytime during runtime. So, there's a number of them, but there's only a few really important ones. But we'll touch on them, and let's go do that right now, and then we can move on from there. Okay, so before we get started, let's take a look at the clock distribution. They have a chart here in the data sheet. So it shows you which parts of the microcontroller are controlled by which clocks. And now you can change the speed of all these clocks. You can disable them, enable them, except for PB clock 1 is for the system modules, and it can't be turned off. But the rest can be turned off or on, and the speed can be changed on all of them, even this system clock one. So it just shows you the distribution. You'll probably have to refer to this as you write your firmware for different things. But we're going to cover the PB clocks here in a minute. So we'll just move down here. One more thing I should mention, there's a fail-safe clock monitor. And so if your system clock fails, it detects the system clock. So if it fails, then it switches over to this BFRC oscillator. And so that's internally generated, and then it triggers a non-maskable interrupt. All right, so that way your firmware can detect that the clock has failed and act on it in some way. And so the BFRC is an untuned 8 megahertz oscillator. So it just is a bare bones oscillator, runs at 8 megahertz. And depending on how you have your system set up, it's probably going to change the speed, but it will keep your microcontroller running until your firmware can do something about it, even if it's shut down. All right. And then it says in sleep mode, both the sys clock and the fail-safe clock monitor halt, and which prevents this detection. All right. Okay, so that's that. Now we come down here to the oscillator control registers, and this is where it gets fun. So the first one we have is OSCON. And so the first thing you see is the setting for the internal fast RC oscillator clock divider. So this, by default, there's no division in the clock. So you can divide up to 256 of the clock, divide the clock speed by 256. All right, so the next one is the dream mode enable. So if the dream mode is enabled, then it's for the core, and in between, it still executes instructions normally, but in between executing instructions, anytime the core has dead time like that, then it goes into a special mode to where it uses less power. So if you need to squeeze out the maximum amount of power savings, then you'll probably want to look at using this mode here. Once again, that's for the core, the MIPS 32 core. All right, then we have unimplemented. And then the sleep 2-speed startup control bit. Okay, so if you have your configuration bits from before, the IESO, which is the clock switchover, the enable, if you have the switchover enabled, then you can use this. All right. And if you have it as 0, then this is going to be 0. So you have to use the selected clock directly if it's set 0. All right, so then more unimplemented. Then you have the current oscillator here. So you have these choices of what you can start with or use as an oscillator. So we have these choices, and this tells you what the current oscillator selection is, okay? So then we have another unimplemented bit, and we come down here, and so now we have the new oscillator selection. So you can be running one of these oscillators, and then you can decide that you want to switch to another oscillator at any time in your firmware runtime. So this would be the new one that you want to switch to. So you have these choices, which are the same choices, but you can switch back and forth between these as at will, basically. So then another important bit is the clock selection lock enable bit. All right. So this can lock your selection so that the firmware can't just arbitrarily, maybe even accidentally switch oscillators. All right, so you can lock it with this bit. All right, so if you do an oscillator switchover with this locked, it's not going to switch. Okay, so that's why when you initiate a switchover, you should also read OSCON and this bit here, or these bits, I should say, to see what the current oscillator then is after your switchover, because it might not have switched over for some reason, maybe because this is locked. All right. So then you have the sleep mode. Almost all the modules have a sleep mode enable bit so that you can turn them on and off when it goes into sleep mode or idle mode. All right, or you can keep them running. So the device will enter sleep mode when a wait instruction is executed, or idle mode. And we'll get into that later too. There's a little difference. All right, so then if the clock fails, it sets this bit, like, and the core throws a non-maskable interrupt. But this bit gets set, and as long as it's 0, then you didn't have a clock failure. So you want to monitor that at certain times in your firmware. And then we have an unimplemented one again. And now this is the secondary oscillator enabled. So if you're going to use a real-time clock, then this will be how you enable it. That's the first thing you want to do, is enable it. All right. Or you can disable it at any time. So then this is how this bit you use to do the oscillator switchover if it's enabled. So in your configuration bits, if it's disabled, you're not going to get a switchover. So this has to be a 1 for this to be able to switch over. Okay. So this will follow this just as the other bit up here did. So when you set this bit, then you initiate an oscillator switch to the specified oscillator that you set in this right here, the new oscillator. Okay. So then that's pretty much it. And so now we need to go back to our code and discuss a few things about startup. Okay, so here we are at our code. And so the very first thing after the configuration bits that you want to do is include the xc.h header file. So this file includes all, well, it defines all the PIC specific register names and the interrupt vector names and all that stuff that you would not normally find in a non-PIC device. So it's PIC specific and it's device specific. And when you configure your project to run with the microcontroller that you've chosen, then it uses that to determine which sections of this XCH is loaded and applicable to your microcontroller. Because some of the different microcontrollers, even though it's the same family, and but if it's a different package, the smaller packages have some reduced modules and stuff like that. There's subtle changes. So you want this file in here so that when you type in this OSCON thing, then it knows what you're talking about. Otherwise, you'll either have to define it yourself or you're going to get an error on your build. So after you include the xc.h, then you're going to want to check to make sure that the PLL is ready. So I do a while loop, and so if it's not ready, it just waits until this says that the PLL is ready and stable. Then you can come out and you can go to the next line of your code. Okay? And that's important because you can have problems and unpredictable behavior if it starts up and the PLL isn't stabilized. All right. Now also, if you intend to write to any of the clock control registers, you have to unlock the system because they have a system lock to prevent arbitrary and spurious changes to the control registers in case there's noise, code error, or something like that. So it's locked, so it can't be changed until you unlock it. So to unlock it, and we will need to unlock it because we're going to change when we set up the core. We're going to have the system unlocked. So we'll just paste this in right here. And so you just, this is one of the advantages of this XCH because this thing called syskey is already defined inside the header file. So it makes it easier so that you don't have to like do register writes and stuff like that. So this is the sequence that you have to write to it in order to unlock the system. And then to lock the system back, you just write in anything that you want in here other than these. So you can write all zeros, ones, 1, 2, 3, 4, whatever you want, and that will relock it. So this will unlock it so that you can write to the control registers. Okay, so next up is the oscillator tuning register for the FRC. It's only for the FRC oscillator. So there's not much to say about it. You can just trim it on either side of the center frequency here to match whatever temperature your device is going to run at, and you can dial in the frequency. That's about all you can do there. Not much to say about it. So then let's move on to the system PLL control register. And so basically there's not a whole lot to say about this one either because we set all the defaults in the configuration bits. So if during runtime you want to override the default values of the configuration bits, then you can use this register to be the SPL con register. You can use it to override your default settings that you programmed in for your oscillator in your configuration bits. Okay, so here is the peripheral bus clock divisor control register. So this is the control for all the different clocks that control different modules. So we have PBX, which is 1 through 7. So PB1 cannot be turned off. It is the system clock. So is what you do is, these are unimplemented, so bit 15. So the upper 16 bits is not even implemented on this register. So this is to enable the clock, and bus clock 1 cannot be turned off or disabled. All right, so this turns your clock on or off. Unimplemented, and then this is when you do the switch the divider number, the value for the division of the clock. You would have to wait for this to be 1 before your code moves on, maybe, depending on your firmware, but that would be a smart thing to do. And another unimplemented set of bits. Then it comes down here, and you have the division that you want to divide your clock by, and you specify which PB clock X. So if you're up here in PB1, then this X corresponds to 1. PB2 is PB clock 2, and so on until you get to 7. All right. So this tells you what some default is for 7. And that's pretty much it. Let's jump over to the code, and I'll just show you what I do and how you implement these registers here. So here's our code, and I will paste in the code for the PB clocks. So this is what I do. And I don't divide a whole lot. I like mine to run as fast as possible. So I put a 0, which means no division. Like the PMP in the COM modules, I have set at 1. ADC is at 0. IO ports at 1. Ethernet at 1. Deadman timer, I don't really use it, but it's at 0. The external bus interface, I don't use it. I could probably turn this one off. But that's how you do it. You set your divisor and then you turn it on. And like before, we said that the PB clock 1, you can't turn it on or off, so you don't have to turn it on or enable it. So that's pretty much it for the divisors. You just have to tailor that to your own needs. But you'll have to set these up in your firmware in the beginning sometime, but in the beginning is probably good. And then we can move on. Okay, so next up we have the slew control, the oscillator slew control register. So this controls the rise and fall time of certain pins, certain signals, mostly used for like SPI, some of the COM stuff. For like IO pins, it's probably not that important of a thing. It would have to do mostly with the serial communication stuff, mostly. But we can go over it real fast. these bits control the system clock division. It has a note here. And then these are the step control bits. Steps are divided by 2, and on and on and on. So 0 is no divisor is used during slewing. And then it gets kind of tricky because these steps are in reverse order during a downward frequency change. This would be for an upward. And that brings us over here where you can disable or enable going to a higher frequency, or you can disable or enable slewing for going to a lower frequency. All right. So then this is the clock switching. When you change the slew rate, then you would want to wait for this to become 0 before you move on. So that, I'm not going to say much about that unless we cover it later on down the line. I don't see it being really important other than with like really fast SPI or something, some really stringent stuff. So last but not least, we have our clock status register. And so there isn't much to it. It just is a register that you can read to gain information about your clock. So the low power RC oscillator is ready or not ready. That's indicated by these bits here. Same with the secondary oscillator. So if you turn on the secondary oscillator, then you want to read this bit to make sure that it is stable and ready. All right, it should be a 1. All right, and then the same thing with the primary oscillator. See if it's ready and stable or not. So you read that bit. And so then the divided system PLL is ready or not. So you'll want to check that. That's the one that we check at the beginning to make sure your PLL is ready and stable. Very important. Then the fast RC has the same kind of thing where you can see if it's stable and ready or not. All right. So that concludes the clock oscillator control registers. And so there you have it. That is the oscillator control registers. So that pretty much is it. So I think I'm going to conclude this video right there. And so the next one, we'll start configuring different things like the flash, wait states, and the core. That's what's coming up next. So I will see you in the next video.